Hi, my name is Alvin Ramos, and this is the part one of the topics of Group 4, which is all about hidden Markov model. But before we start, this is the outline of the topics I will discuss in this video: the introduction, discrete time Markov process, and extensions of HMM.
One well-known and widely used statistical method of characterizing the spectral properties of the frames of a pattern, namely hidden Markov model approach. These models are also referred to as Markov sources or probabilistic function of Markov chains in the communication literature. The basic theory of hidden Markov models was published in a series of classic papers by Bohm and his colleagues in the late 1960s and early 1970s. Implemented for speech processing applications by Baker at CMU and by Jelinek and his colleagues at IBM in the 1970s.
HMM are especially known for their application in temporal pattern recognition such as speech, handwriting, gesture recognition, part of speech tagging, musical score following, partial discharges, and bioinformatics. Consider a system that we describe at any time as being in one of the set of n distinct states indexed by 1, 2, up to n, as illustrated in this figure, where n equals 5 for simplicity. At regularly spaced discrete times, the system undergoes a change of state according to a set of probabilities associated with the state. We denote the time instance associated with state changes as t equals 1, 2, and so on, and we denote the actual state as qt. The stochastic process could be called an observable Markov model because the output of the process is the set of state at each instant of time, where each state corresponds to an observable event. Idea: consider a simple three-state Markov model of the weather. Assume that once a day the weather is observed as being of the following: precipitation, cloudy, and sunny. State model is shown in this figure at the left. We postulate that the weather on day T is characterized by a single one of the three states above, and that a matrix A of state transition probabilities is shown in the matrix at the right. Given the model, we can now ask several questions about weather patterns over time. For example, we can pose a simple problem. What is the probability, according to this model, that the weather for 8 consecutive days is sun, 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 rain, rain, sun, cloudy, sun? Solution. First, define the observation sequence O as the figure below, corresponding to the postulated set of weather conditions over the 8-day period. Calculate the probability of the observation sequence O given the model shown in the lower left. We can directly determine the probability as shown here in the slide. We have considered Markov models in which they corresponded to a deterministically observable event. Thus, the output of such sources in any given state is not random. This model is too restrictive to be applicable to many problems of interest. Section, the concept of Markov models has been extended to include the case in which observation is a probabilistic function of the state. That is the resulting model, which is called the hidden Markov model. Assume that you are placed in a room with a curtain. Behind the curtain, there is a person performing a coin toss experiment. This person selects one of the several coins and tosses it, heads or tails. The person tells you the outcome, but not which coin was chosen each time. Case, we could model the situation with a two-state model in which corresponds to the outcome of the previous toss. In this case, the Markov model is observable, and the only issue for complete specification of this model would be to decide on the best value for the single parameter, let's say the probability of the head. Possible Markov model for modeling the observed sequence of coin toss outcomes is given in this figure. In this case, there are two states in the model, and each state corresponds to a different bias coin being tossed. Each state associated with a probability distribution of heads and tails, and transitions between states are characterized by a separate set of probabilities. The probability of whether the experiment continues with the same coin or changes to the other coin. After some example, we now formally define the elements of HMM. N, the number of states in the model, although
The states are hidden. For many practical application, there's often some physical significance attached to the state or to sets of states of the model. Thus, in the coin tossing experiments, each state corresponds to a distinct bias coin. M. The number of distinct observation symbol per state. For the coin toss experiments, the observation symbols were head or tails. A. The state transition probability distribution. B. The observation symbol probability distribution. And pi, the initial state distribution.